Hello everyone. In this video, I'm going to show you how to do PCA and clustering in R. So we start by clearing out the environment as always. We will be using the US arrest dataset. So let's see what that dataset has. So I'm extracting the names of the states. So it has all the 50 states in there. The dataset has 4 variables: murder, assault, urban pop, and rapes, and each row represents a state. So let's calculate some basic statistics first. So let's calculate that. Notice how different the variances are. So this line of code gives us the variance for each of those variables, and you can clearly see that there's a lot of variances. Then this is why scaling is important for PC. The variable assault, as you can clearly see, has a much higher variance than the others, and if we don't scale it, then it will arbitrarily influence the PC results a lot. But the good thing is we don't need to specifically do anything, but the PRComp function has an argument inside it that can take care of that. So by setting scale equals true, I'm standardizing all the variables to have the mean 0 and variance 1. So I have the principal components, and let's examine that. So this this object that I've created has the standard deviation, rotation, center, scale, and x. So if I want to display the same centering and scaling values using the PCA, I type PROut $center, and the scale step is this. And I want to display the loadings or those z's that I have, the loading matrices. This shows how much each original variable contributes to each principal component. And I have 4 principal components over here. So in other words, let's see what this is. So what the rotation matrix tells us is that it tells us how much each of the original variable contributes to the principal component. For example, if you look at PC1, we can see that which crimes have the strongest influence on this component. And we can visualize our PCA results with a biplot. So the biplot shows both the observations, that is the states, and the variables in the same plot. States that are close together have similar crime profiles, whereas the arrows represent the original variables showing how they relate to the principal component. Sometimes for better visualization, we want to flip the sign. So we run these 3 lines of code. And we get that. But the more important over here is how much, how many components to keep. And so to decide, we look at how much variance each of the components explain. So first, we extract the proportion of variance explained, PVE, and then we create a visualization plot where we first plot how each of these components explain and then the cumulative plot. There you go. So in this example, the first principal component explains almost 60% of the total variation. The second component explains around 25%. The third one is around 15%, and so on. So using this, it gives us a fair idea about how valuable each of these components are individually. And we can use this to decide on how many uh, components to keep. So instead of using 4, we can effectively work with 1 or even 2 to and that will give us almost the same amount of information, at least the important information, as all information like data with all the variables. Next is the matrix completion selection. This is the code here is a little tedious, but this is just if you want to go deeper into it. So I'm just going to run all the things over here. It basically does this, uses the correlation matrices to impute missing values. So what it does is that it first creates a scaled version of the data. I perform PCA on the scaled data. I look at the summary stacks. And then I'm creating a matrix with missing values to demonstrate matrix completion. So I am selecting 20 number of observations to omit, and I'm randomly taking those observations out of the matrix. And then I'm creating a function to approximate a matrix using the single value decomposition method with whatever information is left. And then I am initializing the matrix with missing values filled by column names. And I'm setting up the convergence criteria, and I'm then letting it do it over and over again till everything is done. Not super important for this course, but if you want to play around with this, I'm just keeping it on the script for you to explore this. Finally, we have the clustering. So for this, we are generating a data set. So I'm not going to work with an actual data, but rather I'm going to generate a simple data set with 2 clear structures. So let me create that first. And I'm performing the k-means clustering using km_out function. K-means function. I'm storing the results in km_out. N start equals 20 means it tries 20 random initializations, and then I'm displaying the cluster assignments for each of these observations. But better way of trying it is using the plots. And here we have the green and the red. Each observation represents, like you can clearly see that there are the observation has been clustered into 2 different groups. Now I know that this data set has 2 clear clusters because I've created it. What happens if I try to over classify? So what will happen is that it will take some of these data sets from the proper clusters and will try to force a different cluster over here. Like the blue dots, some of these blue dots should have been in the green ones. Some of these blue dots should have been in the red ones. But because I'm forcing the algorithm to divide it into 3 clusters, it will do this. Then we have the hierarchical clusters. So in hierarchical clustering, we use the hclust function, which takes 3 arguments: the distance, like 2 arguments, the distance and the method. So first we do the complete method. Then we can also do the average and the single, and we can visualize the dendrograms for each of these different methods. And you can see that there is some differences over here. And then we can cut the dendrogram to get two clusters using the cut tree function. So this function takes in two arguments again, the tree that you want to cut and the number of clusters that you want to return. So this is basically it, right? Like, one, if you understand the theoretical side of it for the art's perspective, for this side of the story, there isn't much to understand because you don't have to manually create these figures. You already have the functions. You just need to understand what is happening behind the scenes so that you can plug in the right numbers and write the right arguments. So that's basically it. So it's, as far as doing these stuff in R is concerned, it's very, very, very straightforward. What you really need to focus on is understanding what is happening on the theoretical side. So once you do that, you already have the functions built in and ready to be used. You can just use them and get the results. So that's about it. So that's all as far as the R's side of this unsupervised learning is concerned. Again, do not hesitate to reach out to me if you have any questions. Thank you.